Hello, AP Calculus AB students, and welcome back to yet another lesson in Topic 1 on limits and continuity. We're going to finish up Day 6's lesson, and this brings us to Day 7, which is Horizontal Asymptotes, Part 2. So last class we really set the stage with how to find horizontal asymptotes. Those are our limits at positive and negative infinity. And we also learned a little bit about function dominance. Today we're going to broaden our horizons and come up with a few more complicated equations and discuss a couple specific cases that you might not have considered in the past. So for our opener, let's go ahead and find any asymptotes that might exist for the function below, and then go ahead and check your answer using your calculator. And by your calculator, I really mean your graphing calculator. You'll make a graph and see if you're right. So let's get that done, and then unpause, come back to this, and we'll see how you did. All right, we're back. Well, let's go ahead and try what most of my students in the past try to do, and I think it's a good strategy. They say, okay, let's find the limit as x approaches infinity of square root of x squared over x plus 2. And then they look at those and go, okay, well, let's go ahead and simplify. And I'm still going to have x's in this. I haven't evaluated a limit, so we still need the limit. And they say square root of x squared is x over x plus 2. And then this really just becomes 1 plus 2, right? We simplified, have no more x's. We can just find our limit as is, just constants, and we get 3. We say, cool, limit's 3. And then, knowing that I'm going to ask you to do it, hopefully you also check the limit at negative infinity. And I'll just go through those same steps again, because why not? Consistency. You can always fast forward if this seems like I'm just doing the same thing twice, because I kind of am, and 1 plus 2 is 3. Great. So hopefully you've concluded here that the asymptote for this function is y equals 3. But then, even more hopefully, you graphed this equation on your calculator and you saw something quite weird happen. Okay, I have this graph prepared up here. Here's the graph. Now Desmos actually does a pretty poor job, excuse me, of showing this graph. Desmos has this weird piece in the middle, but you'll notice that the point just bounces back and forth here. There is not actually a vertical line in the middle of it. The graph is just at 3 and at 1. That is it. And then right at 0, since you can't substitute in 0, there would actually be a hole. This is strangely a jump discontinuity, though. So it makes sense that we got an asymptote of 3, because if you look on the right side, this line, well, it's maybe not even accurate to say approaches 3. This line is at 3. In fact, there's an interesting debate out there about if horizontal lines are their own asymptotes, right? If you graph y equals 5, does that have an asymptote at 5? Well, calculus would suggest yes, because, and I'll jump back here as a little side note, right? If you're like, find the asymptote for y equals 5, you'd find the limit as x approaches infinity of 5. And we know that the limit of a constant is just itself, so we found an answer. And this is the definition of a horizontal asymptote. As x approaches infinity, if you get a value, that is the asymptote. And so that's why I also say that it's maybe incorrect to think of the fact that a horizontal asymptote is a line that your graph never touches. This clearly touches the asymptote everywhere. And it's even kind of weird to talk about it as approaching. All right, some people will say at infinity your graph approaches the line but doesn't touch, because at infinity the line exactly touches the asymptote. So if we're just going by the pure definition here, there is certainly an asymptote. However, there is also an issue. The issue is we got an asymptote to the right at 3 and to the left at 3. And on this graph to the right it's 3, but the left it's positive 1. So how did we come up with positive 1 instead of 3? I mean, this is the issue, right? This is moving towards negative infinity. How come that's 1 instead of 3? Well, the mistake you probably made is with simplifying, right? You might have thought that the square root of x squared is equal to x. And that's actually false. Or it's not completely false, but it's somewhat false. And so we're going to go ahead and prove that right now by graphs. Because if we say these are equal, then the graph of y equals x squared, which is the left side, and the graph of y equals x should be the exact same graph. Y equals x, we know, starts at the origin, up 1 over 1, looks something like this, give or take. But then y equals the square root of x squared, we're going to try to graph without simplifying. And so when you do that, we substitute in 0. 0 squared is 0. Square root of 0 is 0. Substitute in 1. 1 squared is 1. Square root of 1 is 1. 2 squared is 4. Square root of 4 is 2. And so on and so forth. So this right side here definitely looks like it matches up with the green graph. But then check out the left. When we substitute in negative 1 squared is positive 1. And the square root of positive 1 is 1. Negative 2 squared is 4. Square root of 4 is 2. And what you'll notice ends up happening here is we end up with this equation, which is, or this graph, which is a graph you've seen before. This is actually equal to the absolute value of x. Now, the reason in the past that you guys have always simplified this is because we usually just look at positive numbers, and it's easy just to say that these are true for positive numbers. This is a true statement for positive numbers, right? But so we should notice, though, that y equals x, the green graph, only equals y equals x squared for x's that are greater than or equal to what? Greater than or equal to 0, right? That gives us this right side of the graph. Those are definitely the same. However, for x less than 0, right, and I'll circle those two, it should be pretty clear that they are not the same. Okay? So what function does match y equals x squared for x less than 0? So we have two questions to answer. First, y equals x squared is not the same because this graph is always positive. And we're always positive because you're squaring a number positive and then taking the positive square root. There's no plus minus that's implied in front. If you have a square root, it's always a positive answer. Versus this guy is going to be negative for x less than 0. So therefore, the function which best matches y equals x squared just for being less than 0, just this guy over here, what's a really basic function that would match that over there? Well, I think it looks exactly like this function, but just reflected over. And so couldn't we say y equals negative x, right? Y equals negative x looks like this, but it would definitely match our square root of x squared function for x is less than 0. And you can even see this prepared over here, right? We have y equals the square root of x squared. And then we can show this as a piecewise function where y equals x tackles the right side and y equals negative x tackles the left side. In fact, that actually answers this question up above earlier because you might have said, whoa, if there's a jump discontinuity, didn't you tell us that jump discontinuities happen with piecewise functions? And that's true, I did. This is actually a piecewise function in disguise. That square root of x squared is this piecewise part. So that's why you have a jump discontinuity as a side note. But that means then, if you're finding the limit as x goes to positive infinity, right, these are certainly x's that are greater than 0, then the square root of x squared graph is the same as just the graph of x. And so when you find the limit as you go to positive infinity, it's positive infinity. However, when you find the limit as you go to negative infinity, those are for x's less than 0. And so when you simplify the square root of x squared, it's not okay to say that it equals x. Those are not the same graph. You actually need to say it's negative x. Then when you go to negative infinity, you go negative infinity. It actually comes back to positive infinity again, which makes sense if you look at this graph. This goes up, this goes up. They both go to positive infinity. So let's go ahead then and jump back and fix our horizontal asymptote in the opener. And the fix is a pretty easy one. We're just going to focus on this purple equation. The black equation is correct. As we went to positive infinity, the square root of x squared is the same as x. Negative infinity, the square root of x squared is not x. It is negative x at negative infinity. And so this actually simplifies to become negative 1, and negative 1 plus 2 is positive 1. There is our other asymptote. This question does rear its ugly head every now and then on the AP exam. I would guess probably every other year or so you see something like this on the multiple choice, realizing that positive infinity versus negative infinity have different simplifications of the square root of x squared. And we'll see this a few other times throughout this year, so hopefully it'll stay fresh in your brain, but I thought it was worthwhile spending a little bit of time on that discussion. For now, let's go ahead and jump to our next page and our next style of an example. Okay, so last class we discussed the idea of function dominance in a quotient. And remember, quotient just means something divided by something as x went to positive or negative infinity. However, that quotient was always written as a single term in the numerator and a single term in the denominator, right? It was like e to the x over x. Single term up here, single term down here, no addition and subtraction. But there are, of course, many functions that are more complicated than that. So what if we had a function that had multiple terms in the numerator and multiple terms in the denominator? Okay, let's go ahead and try and find those horizontal asymptotes. Right? You say, okay, let's find the limit as x approaches infinity of f of x. So I'll rewrite this guy really quickly, like so. Lovely. And then 2x squared plus 4x minus 5. Okay, so we end up here and we say, okay, well, this is a little bit strange. We can't simplify anything, right? We can't like start crossing off things with addition and subtraction. That's a no-go. So what can we do? Well, you might say, well, let's use that little thinking corner from the other day and let's just substitute infinity. So we get 3 times infinity squared minus 2 times infinity plus 6 over 2 times infinity squared plus 4 times infinity minus 5. Uh-oh, this is going to have some issues. Now we have those different sizes of infinity, because if you square infinity and then multiply it by 3, it's infinitely large. If you do 2 times infinity, it's also infinitely large, but a different size of infinitely large from the other one. And then to complicate matters even more, you have something going on in the denominator. So this is, and as soon as we see infinities over infinity, indeterminate, which means we need to do more. Now, again, our do more could be factoring, but I'm pretty sure I picked these so that they don't factor. So that's not going to help. And so really our other do more for limits at this point is dominance. So let's backtrack. Let's go back to the idea of dominance. Let's look at a parallel problem, and then we'll come back to this one shortly. So when substituting in infinity, similar situation as yesterday, different sizes, and so our limit is indeterminate. There we go. So we're going to look at 4 different functions, and they are all different, right? We have e to the x plus 1, e to the x plus x squared, and e to the x plus the natural log of x. Okay, so if we look at those graphs, and I have them prepared for you right here, they are clearly different graphs, right? If you look at when x is 0, this guy has a y value of 2. These two share a y value of 1, and this one, probably the natural log one, just goes to negative infinity. It's clearly different there. And the y values are all certainly different here. Okay? But then what if I started going to the right a bit? And I actually run out of this graph, so I'm going to zoom out a bit, and maybe we'll zoom back in up here. Okay? So here's this guy, 1, what are we looking at over here? This is 3. So I don't even know what our scale is looking like here, but that's okay. We'll say 3.6-ish, right? Now it only looks like we have 3 graphs here. There are 4, but some of the graphs are just kind of on top of each other, so it looks like they're pretty much the same. So I'm going to zoom out a little bit further and kind of go up, and then we'll maybe zoom back in over here. There we go. Now this is when this is approximately an x value of 5, right? Give or take about 5. Looks like there's only 2 functions. And would you say that they're very different from each other? Not super different, but you get the idea. So I'm going to zoom back out, go way up here, and then we'll zoom back in. And now, is there really much of a difference between these functions? Well, not really at all. I mean, at 6.78 or so, it looks like all 4 functions are kind of right on top of each other, and that's only for an x value of 6. So what do you think would happen if I went to an x value of 100 or 1,000,000 or infinitely large? Would you even be able to tell the difference in these functions? And the answer is no. As you go far enough out, the dominant terms of the functions take control. So if we jump back here, can you identify the dominant terms here? Right? Our dominant term for each of these, I believe, is going to be e to the x. Right? If you remember our order of dominance, e to the x is much more dominant than x squared or than natural log of x. Right? E to the x is so much bigger than all the rest that at infinity, you'll see the graph of e to the x, and this adding 1 or adding x squared or adding natural log changes it so little compared to e to the x that it pretty much doesn't even show up. In fact, at infinity, you could say that the limits of these four functions are equal. And so what that means is at infinity, you can even say they're the same function. You could ignore the 1, the x squared, the natural log of x. You could just say that they're all the function e to the x at infinity. Not anywhere else, but if you're infinitely large, there is no difference in those four functions. So how would you describe the differences at positive infinity? I would say there are approximately no differences. And so that's really important. This allows us to simplify complicated functions at infinity. So what does that mean? Well, if we go back to this again, then let's go ahead and simplify this function. So I'm going to find the limit as x approaches positive infinity. We'll rewrite this a couple times. 3x squared minus 2x plus 6 divided by 2x squared plus 4x minus 5. And I'm going to say that the numerator, which is this parabola, 3x squared minus 2x plus 6, that is no different than the parabola 3x squared at infinity. Because this parabola, this x squared term, is so much more dominant than the x term, and adding 6 to infinity changes it negligibly at all, right? That we're just going to take the most dominant term, usually identified by the largest exponent, and say that's approximately or exactly at infinity equal to that more complicated term on the left. And then if we work the denominator, same idea. 2x squared is much more dominant than 4x or negative 5, so this is just 2x squared. And it is okay to put an equal sign here. You might say, but this graph and this graph aren't the same. You're right, but they are the same in the eyes of limits at infinity, so we can keep that. Now, if you didn't have the limit here and you just said those were equal, you'd lose a point. That's not true. Those are not the same graph, but this is the same value. And now we can simplify, can't we? This is just the limit as x approaches infinity of 3/2, and the limit of a constant is always the constant. Nice. Now, if we wanted to do the limit as we approach negative infinity, I'm going to save myself from writing this fraction. It's a little obnoxious. I'm just going to say f of x. And then I'm going to quickly simplify. I'll do the same thing as we approach negative infinity of 3x squared over 2x squared. Those are true statements. They are the same limit. And then these cancel, and we end up with 3/2. Great. We actually got the same limit both times. Okay, and if you look at the graph, which I do have prepared here for you, hopefully we're correct. On the right side, we are approaching, I bet if we went out here, we'll approach 1.5, which is 3/2. Nice. And on the left side, I bet we will eventually also approach 1.5, and it looks like we do. Now, you will notice we got the same answer here. And it actually turns out, and we're going to mention this down below, that this is called a rational function. Rational functions, if they're just made up of polynomials, x squared, x cubed, x to the fifth, not square roots, not natural logs, but just nice polynomial functions, they will always have the same end behavior at both positive and negative infinity. So if you're asked to find horizontal asymptotes here and you don't have time to do both, or you just know the shortcut, you just have to do one of the limits because both of them will be the same. Now again, that is certainly not always true. We'll see many more examples where there are two different asymptotes, but it is always true for rational functions with polynomials. And one other fun side note, finding this asymptote here of 3/2, we actually did a technique that you've been using since Algebra 2. Do you remember how to find horizontal asymptotes from Algebra 2? Your teacher probably said, look at the largest exponent. There we go. Find the largest exponent on the bottom, make sure they're the same, and then just divide the coefficients. And that will give you your asymptote. And they're right. Now what they're really doing is they're showing you dominance, but you don't talk about dominance in Algebra 2. So just either way, keep that in mind, and also keep in mind that that will not always work if your functions are not nice polynomials. In fact, we should probably see one of those on the next page. So, example 2. Find the horizontal asymptote for the function below. You can use dominance here, but you must evaluate both limits, so positive infinity and negative infinity, because although 2x plus 3 is a polynomial, This square root is not. And so square roots might not have the same end behavior at positive and negative infinity. So why don't you go ahead and try example 2, and then once you're done, unpause, and we'll see how you did. Good luck. All right, let's get to it. We're going to find the limit as x approaches infinity of this guy, 2x plus 3 over this old friendly square root. Now, we should know that we're not allowed to distribute a square root through addition and subtraction, so we can't simplify there. But with dominance at infinity, what we can do is say, instead of 2x plus 3, the 3 does pretty much nothing at infinity. That's pretty much just the same as 2x. And the square root of x squared plus x minus 5, adding x and subtracting 5 at infinity is negligible to squaring infinity. So I think the square root of x squared is the most dominant term there. Now, let's simplify. The limit as x approaches infinity, 2x isn't going to change, but the square root of x squared is x at infinity. And then I think we can see that this simplifies to 2. We say, great. A horizontal asymptote for this graph is y equals 2. So at the right side of the graph, we should see 2. But what about the left side? Well, let's do the limit as we approach negative infinity of just plain old f of x. You could write this again. I'm just being lazy or efficient, depending on who you ask. And let's simplify this down a bit again through dominance. So it's 2x over the square root of x squared. And then we can simplify the square root of x squared into what? Oh, don't forget the opener. At negative infinity, the square root of x squared is actually negative x. Then, if we simplify, we end up with negative 2. Let's double check our graph to make sure I'm not lying to you here. We have this guy looking pretty good. It does look like we're approaching negative 2 on the left and positive 2 on the right. We did it! How exciting! Okay, example 3. Looking at the function below, we can see that it is also not made up of polynomial functions. We have this 3 to the x and 3 to the x. These are exponential functions. Okay? That means we also need to look at 2 different limits, positive infinity, negative infinity. As a heads up, this problem, or at least the format of this problem, is somewhat infamous, right? Negatively famous, infamous, yeah, for being the only multiple choice question, to my knowledge, that's ever been thrown out from the AP exam. The AP College Board creators for the test put it in there and said, oh, this is a good one to find horizontal asymptotes on. But overall, nationally, the students did so poorly on it, they've never done as bad on any other question, that they said, oops, we need to throw this out. And then they put out all sorts of materials and said, okay, teachers, you need to teach these a little bit better. Your students did not do well here. And let's see if we can understand why students didn't do well. Okay, so let's find those asymptotes, then come back and we'll see how you did. Ready, set, go. All right, so I'm going to show this a couple different ways, but I think at positive infinity, we'll all pretty much do it the same way. So as we approach positive infinity of this guy, okay, through dominance, what's more dominant between 3 to the x, a crazy fast-growing exponential function, or just the constant 4? Well, I'm pretty sure 3 to the x is more dominant. And same thing down here. There's a negative, but still very dominant, right? Negative infinity, positive infinity, much more dominant than 1. And then I think if you simplify these, you'll say, oh, that's negative 1. Great, there's our asymptote. Most students stopped here. When I looked at these results, they just said, cool, the asymptote's negative 1. But they forgot to consider, or they weren't sure how to consider, the limit at negative infinity. Now again, I'll give you 2 ways to do this. One ties into what we did yesterday, and then the second is something new, but is a pretty cool little identity that'll help us out. So what you might realize or remember, and it's okay if you don't, because I think you'll like the other way a little more, is at negative infinity, because our exponential graph, right, 3 to the x's growth, at negative infinity, this graph goes essentially to 0. So the question becomes, what's more dominant at negative infinity, 0 or 4? And 4 is, right? It didn't quite get to 0. It's just very, very close to 0. 4 is way larger than that. So we end up with 4, and then the same thing, 1 over here. And so this gives us a second asymptote of 4. Now again, if you didn't like that way, here is a second option. And I think the second option is pretty cool. The second option is going to tie directly into what I've stated down here, so we should probably discuss this first and then we'll go back. If you're evaluating a limit at negative infinity, and you're like, there's weird stuff that happens at negative infinity, I don't really like that, then the following limit identity can be pretty useful here. And that's the identity that the limit as x approaches negative infinity of a function is the same value as the limit as x approaches positive infinity for f of the negative x for that function. So in regular person terms, instead of calculating the limit as x approaches negative infinity, substitute in a negative x everywhere you see an x, and then calculate the limit as x approaches positive infinity. Let's go ahead and try that. So up above, we'll start with the same part. We'll say, okay, we're trying to find this, but that negative infinity makes us sad. So instead, let's just find the limit as we approach positive infinity. Things seem to be a little more predictable there, right? 4 plus 3 to the negative x over 1 minus 3 to the negative x. So again, I went through and I replaced our x's that were here with negative x's. Now there's a few reasons why this works. One is that graphically what's happening is when you substitute in a negative x for all the positive x's, it reflects your graph over the y-axis. So it would cause this one to go the other direction. And then you could find your limit at infinity. Notice that we get 0 over here, which was the same thing as before. The other thing you could say is you're just switching it around. So negative infinity of the function will be the same as positive infinity of the negative function, right? Same idea, however you'd like to think about it. But how do we finish calculating this? Well, we might want to think about substituting in infinity here. Or if you wanted, you could remember that to deal with a negative exponent, you just do 1 over that term with a positive exponent. We, by the way, are not allowed to move this to the denominator because it's attached by addition here. You'd have to move the whole thing, but this doesn't have a negative exponent. It's the whole issue. So we just make it its own fraction within a fraction, a complex fraction, if you will. And we'll do the same thing over here. Oops. Now, if I put this, I would have lost a point because I forgot the limit. So we'll just be a little lazy here and squeeze in that limit. Perfect. All right, now how do we calculate this? Well, let's bring back our thinking corner. You didn't think that was gone, did you? And we'll pretend that if we substitute in infinity, what happens here? Well, 3 to the infinity is infinitely large. A constant over infinity, oh, that's 0. Thanks, thinking corner. Okay, so this tells us then that we'll get 4 plus 0 over 1 minus 0, which is, again, 4. And you should also probably notice that this trick works for this guy up above too, right? If you replace all the x's with negative x's, you would get 2 times negative x over the square root of negative x squared. And so we'd end up with negative 2x over the square root. Negative x squared is just x squared. And then we end up with negative 2x over x, which is negative 2. So again, if you get to negative infinity and you can't remember the tricks, replace the x's with negative x's and just find positive infinity and you'll be fine. All right, so to finish off class today, I have 4 problems for you. And I am going to ask you to work with 4 different partners. The reason why is sometimes your partner will have a different approach to a problem that you might like more than the way I taught it, and it also helps bring others who are still a little bit confused back up. And it also helps remember the information for you, or help you remember the information by teaching it to others if necessary. And it lets you socialize a bit. So, for each problem, you're going to work with a partner. You'll do the work on your paper. They'll do the work on theirs. You can help each other, or you can work individually in parallel but in silence and then discuss your answer at the end. Once you guys agree on an answer, sign each other's paper, somewhere on the bottom. You can do a little signature down here, whatever sounds good, and then move off and find a new partner. Right? So 4 different partners, 4 problems. We just have a nice variety of limit questions here for you, and we'll see what you've learned over the last couple days. So go ahead, and if you guys do ever get stuck, you can unpause this and see how to do it. But hopefully you can get through all 4 of them without me, and then come back together to check your work. Ready, set, go. Now, you might have looked at the first problem and your brain might have gone a little blank, or maybe that's your fight or flight reaction because you said, oh my gosh, there's a cosine. Cosine wasn't in our list of dominants. So how do we decide what's more dominant between these two? Well, the answer is A, you should actually know how to tell which one's more dominant. We'll get into that later. But B, you actually can't use dominance on this problem because we're not looking at the limit as x approaches infinity. We're looking at what happens as x approaches 0. Dominance only works, you can only simplify parts of your function at infinity. That's when dominance is relevant. For this is bringing us back to the basics. To find the limit as x approaches 0, we should use direct substitution. That's always our first step. I'm going to leave the equals off in case anything weird happens. I'll put it back in, but we don't need the limit because now we're substituting in. We're finding an actual value at a point. We're going to see if we get something here. Well, cosine of 0, do you guys remember that one? Cosine of 0 is 1, isn't it? Right? If we start over here, this is the point 1 comma 0, and cosine is always the x. Okay, plus 3, anything to the 0th power is 1 over 2 times 1. I'm getting 1 plus 3 is 4 over 2. I'm getting an answer of 2. I think that's our final answer, just 2. Now, I did mention, this is just a nice little side note here, that you should be able to find the limit at infinity for this as well. Right? As we take the limit as x approaches infinity and we bring back our idea of dominance here, what is more dominant between a trig function and e to the x? And the answer, if you phrase it that way, is I'm honestly not sure because I said a trig function. But let's be specific here. We're talking about cosine. That one, I'm definitely sure between dominance of e to the x and cosine of x, I know which one it'll be because the graph of cosine just bounces back and forth. It's your cosine wave, and the maximum of a cosine wave is just 1. So at infinity, cosine doesn't approach a specific value, but at infinity, the biggest cosine we'll ever get is 1, smallest is -1, while e to the x is infinitely large. It's hanging out here at infinity, just kind of looking down at this guy smirking and saying, I'm way larger than you. Yeah, I'm pretty confident at infinity, e to the x is going to be way more dominant than cosine of x. So I'm pretty confident in saying this equality is true. And then simplifying and just saying our answer is 3/2. So there would be an asymptote of this at 3/2. What about negative infinity, though? That's a very interesting conversation. A few weird things happen here, but cosine of x plus 3e to the x over 2e to the x. At negative infinity, cosine of x is still doing its bouncing thing, back and forth between -1 and 1, -1 and 1, not approaching anything. But as we've discussed several times now, these exponential growth functions at negative infinity, right? At negative infinity, they're getting closer to 0. They're pretty much just not there. So this limit then is going to be just cosine of x, right, plus 0 over 0. And that's kind of a weird limit. We have some number over 0, which in the past we've learned means does not exist. But even if there wasn't a 0 there, let's say that there was like a 4 or something, cosine never approaches a specific value, right? It's that cosine wave. And if we don't approach a specific value out at negative infinity, then the limit doesn't exist. So I'm pretty convinced in 2 ways that this limit will not exist and there is no horizontal asymptote to the left. Take the reasoning either way. Let's look at the graph. So here's my graph. It's in black right here. We found the limit as we approach 0, right? That was initially as we approach 0, the y value is 2. Yeah, I'm pretty sure that's the right answer. To the right, it looks like we definitely approach 1.5 pretty quickly. E to the x blots out cosine and just says, I'm in control here. But then on the left side, look what happens over here, right? We just are bouncing back and forth and so high up because what ends up happening is e to the x is like 0.00000 when you 1, and when you divide by a small decimal, your answer gets really, really big. So cosine is actually getting bigger and bigger and just bouncing up and down forever. Definitely not approaching a value. Definitely no horizontal asymptote on the left side. Okay, let's move on to problem 2. Identify all vertical and horizontal asymptotes for the function below. Ooh, blast from the past. Vertical and horizontal? Let's start with horizontal because we've been focusing on that. We know we'll need to find the limit as x approaches infinity of f of x. Well, to do that, we've got this function on the top and this function on the bottom, and they look pretty complicated. I'm not quite sure what's the most dominant or even what to do here. But one thing I do know, or my algebra skills are decently strong, couldn't we multiply all of this out, right? Just doubling, distributing, or FOIL, whatever we call it. And we could do the same thing for the denominator, right? 2x plus 1 times itself. I'll multiply all that out as well. So I'm going to go ahead and find the limit as x approaches infinity of the numerator. I'm going to do the x's first. That's negative 12x squared. And then I see negative 32x. And this looks like positive 15x. And I'll finish it with positive 40. And then the denominator, this one's a little easier, right? 4x squared, 2x, and another 2x is going to be 4x, and 1 times 1 is 1. Cool. Now we have a limit of two polynomials. This is a rational function, and we can use dominance, right? My most dominant term will be negative 12x squared in the top and 4x squared in the bottom. These cancel. We end up with negative 12 divided by 4, which is negative 3. Do I need to find the limit as we approach negative infinity? Well, you can, but because this is a ratio of two polynomials, the limit will be exactly the same. So I think my horizontal asymptote is going to be at y equals negative 3 on both sides. Let's do the vertical. Vertical asymptotes have to do when the function becomes undefined. And we discussed on the vertical asymptote page the difference between a whole and a vertical asymptote. However, it all has to do with the denominator down here. Wholes or removable discontinuities occur with these rational functions when something in the top cancels out one of those factors in the bottom. But these factors are clearly not equal to what's on the top. Nothing's going to cancel. I think that there's just going to be vertical asymptotes here. So the question becomes, what makes the denominator equal to 0? And an easy way to do that is with algebra. Let's set the denominator, 2x plus 1 times itself, equal to 0. These are the same functions, so really we're just solving 2x plus 1 equals 0. And subtract 1, divide by 2, I'm getting negative 1/2. This tells me then that there's going to be a vertical asymptote at x equals negative 1/2. So I think there's one vertical asymptote and then a horizontal asymptote that travels throughout. Let's check our function and see if we're right. Right here. Horizontal asymptote looks like we're approaching negative 3 on both sides. And our vertical asymptote, yep, this does cross over 0, doesn't it? Yeah, we get up here. Yeah, we're on the negative side. Yeah, I'm pretty confident that negative 1/2 right here would perfectly split those functions and be our vertical asymptote. Negative 3, negative 1/2. Well done. Problem 3. Oh, a piecewise function? Where did that come from? Identify all horizontal asymptotes for f of x. Now, what I've seen people do in the past is they go through and they try to find the limit as x approaches infinity for all three of these pieces of the piecewise function. And I don't think that's what we want to do here. The reason we don't want to do that is because we want to find the limits of f of x. And so the function is called f of x, and I'll use two different sides here just so I don't run out of room. We're going to find the limit as x approaches infinity of the function called f of x, right? That's what they asked us to do. And we're going to find the limit as x approaches negative infinity of f of x. There are two limits here, one to positive infinity, one to negative. So to positive infinity of f of x, we need to look at the three pieces or branches that make up the piecewise function and decide what's in control for really big x values. Well, this rational function is in control for negative x values less than negative 3. This line, mx plus b, is in control only for x's between negative 3 and 0, and this ratio of exponential functions is in control for x's greater than 0. Positive infinity is definitely greater than 0, so when I'm finding the limit as x approaches positive infinity, we're really just finding the limit of 2 to the x over 2 to the x minus 2. That's the only branch that matters at positive infinity. And so, through dominance here, we want to go through and say, well, 2 to the x is its own function. 2 to the x is much more dominant than -2, and these cancel and just give us 1. So there's one of our horizontal asymptotes. Notice that I started with the limit as x approaches infinity of f of x. I think that's an important step. That tells the grader that you know you're working with this whole function first, and then you kind of dial in on the specific branch, showing that those are related. All right, let's do negative infinity, but I think you guys get the idea now. As we approach negative infinity, what's in control? Well, that's got to be this function up here for x's that are less than -3. So that's our 2x squared plus 5x minus 3 over x squared plus 4x plus 3. Okay, and as we simplify down through dominance here, 2x squared and x squared, and they cancel and leave us with 2. So I'm seeing 2 horizontal asymptotes for this piecewise function. On the right side, y equals 1. On the left side, y equals 2. All right, last problem for the day. The function f is given by the equation f of x equals ax squared over x squared plus b. So this is a rational function, 2 different polynomials, parabola, parabola. The figure to the right shows a portion of the graph of f, including the asymptotes. Right? We can see our asymptotes here. We have a vertical asymptote at x equals -2. We have a horizontal asymptote at y equals -3. And we want to know the possible values of our 2 constants here, the a that's out front and the b that's in the denominator. Well, the trick here, and it makes sense because it's in this lesson, is all about the vertical and horizontal asymptotes. Right? The horizontal asymptote, we'll start with that since that's the focus, runs all the way across, and we know to find a horizontal asymptote, you find the limit as x approaches either positive or negative infinity. It doesn't matter because they're just both polynomials of f of x. And we even know the answer to that. I know when I find this limit, the answer has to be -3. It's on the graph. So let's just work down here. As x approaches infinity of f of x, which is ax squared over x squared plus b, that answer has to be -3. Keep working with the left side. The limit as x approaches infinity. How do we find the limit of this? Well, we do dominance. Dominant term in the top is ax squared. What's more dominant, x squared or some constant b? Well, x squared is more dominant. And then these cancel, and it leaves us with just a equals -3. Okay, so I'm going to start to fill in my function up here because I actually know what they equal now. This will be -3x squared over x squared and plus something. Okay, so let's go ahead and find that b value. How do we find the b value? Well, the b value is in the denominator, and we know that the denominator controls where the vertical asymptotes are. So let's take the denominator. We know x squared plus b, right? That is going to be -2. What makes it -2? Well, what they're telling us is that when we substitute -2 in for x, the denominator becomes 0, right? You're not allowed to use -2. It turns the denominator to 0. So this becomes 4 plus b equals 0, which tells us that b equals -4. So up here, this becomes x squared plus -4. Now, you could have written that as x squared minus 4, and that might make even a bit more sense to you to see that this becomes x minus 2 times x plus 2 if you factor, right? And you're looking at this and you might say, well, wait, I see an asymptote at -2. What about at +2? Well, and that's why they just showed part of the graph. So it's kind of, I think, a little sneaky here, because I would argue that there should be one over here at +2 as well. But maybe we just can't see the part of the graph, but it doesn't cross. I don't know. Maybe it's not a perfect problem, but I still think it's a very clever one, knowing that we can find the limit to find one value, and we can work with the denominator to find the other. Okay, so either way, I think that works out quite well here. This is the end of our horizontal asymptotes lesson, finally. We only have a couple lessons left in this unit, maybe like 3-4 lessons, give or take. But again, we're spending a decent amount of time on this because limits really are the foundation for the rest of calculus. There's only one unit on limits, just topic 1, and then everything else focuses on 2 other topics in calculus, but limits are what make it all work. So, thank you as always for tuning in, and I'm excited to have you guys back for day 8 next class.